Hello, and welcome to my IPC video project for Unit 5. Today, I will show you how to cook fettuccine alfredo using the laws of thermodynamics. So, you turn on the burner, wait a few minutes, and when all those small bubbles appear, you're ready to get cooking. As you wait for the pot of water to boil, however, there's an extremely complex process going on. First, the liquid on the bottom of the pot closest to the heat source starts to get hot. As it does, it rises. The rising hot water is replaced by the cooler, more dense water molecules. These water molecules in the pot continually exchange in this way, thanks to gravity, eventually warming the entire pot of liquid. This is known as natural convection, the movement of molecules through fluid, which is a primary method of heat and mass transfer. Additionally, the pot itself is an example of conduction, where the heat is flowing directly through the stationary matter. The stove is radiating off heat. So even an everyday activity like cooking noodles involves a lot of physics. Next, we do know a few things about our friend water. Water has a fairly high latent heat of vaporization, so we have to make sure to turn the stove to the highest heat level. I make sure I add just enough water to cook the noodles, so the amount of time to heat up the water is shortened, as specified in the equation Q equals mL, where Q equals the heat transferred to a system, m equals mass of sample, and L equals the heat of transformation. Next, I also added table salt into the water, which will cause the temperature of the water to rise, making the noodles cook much faster while also adding flavor. Boiling is a very efficient heat transfer process, and in this case, boiling transfers the heat from the fire on the stove to the water that will cook the pasta. It seems straightforward enough, but natural convection is not enough to heat the water, as it does not yet provide the bubbles needed for the pasta. To get those bubbles, you have to wait long enough for the bottom of the pot to get hotter than the boiling point of the water. When the boiling point is breached, you finally begin to see the tiny bubbles of water vapor you've been waiting for. The bubbles rise due to buoyancy and then collapse as they reach the denser, relatively cooler water at the surface of the pot. This motion not only helps to move the water around more quickly, but the bubbles themselves transfer heat energy as well. In its basic sense, cooking is all about breaking and forming chemical bonds in food, which in turn changes its properties. Set the pasta aside while we cook the chicken. To cook the chicken, put some oil in a pan over low to medium heat. Place one chicken breast on the pan, when hot, and season with salt. This is a type of deep frying. Deep frying is just the process of simmering the chicken in hot fat. I know, gross. However, there is thermodynamics behind the process. The fat appears to boil when the food is immersed in it, because the water in the food boils and produces steam. As the water near the surface of the food being cooked is evaporated and the surface crusts over, sealing the remaining water in the interior of the ingredient, the bubbling ceases. While the water evaporates, the temperature of the fat will be lowered if the amount of steam is relatively high in comparison to the amount of fat. The transfer of heat from the pan to the chicken occurs by means of convection, much like the boiling process. This process occurs at both the interface of the interior of the pot and the liquid, where the liquid, in this case the oil, is heated and the pot surface is cooled in an attempt to reach equilibrium, and at the interface of the liquid and solid ingredients, where the ingredients are heated and the liquid is cooled in another attempt to reach equilibrium. Hot air, which has lots of vibrating molecules, transfers some of its energy to the exterior of the meat. This energy excites the molecules on the surface of the meat, and then they transfer heat to the molecules inside it, and so on, slowly passing the energy towards the center of the meat like a wave of heat. Because meat is about 75% water, and water is a good insulator, especially when trapped inside muscle, the heat moves inward because physics dictates that the meat seeks equilibrium in an effort to make the temperature the same from edge to edge, so most of the meat is cooked by the meat, not by the air. In fluids, heat is often transferred by convection, in which the motion of the fluid itself carries heat from one place to another. Another way to transfer heat is by conduction, which does not involve any motion of a substance, but rather is a transfer of energy within a substance, or between substances in contact. After the chicken is cooked, cut it up into bite-sized pieces and put it back into the pan to keep it warm. Then start to heat up the pasta sauce in a saucepan. An argument can be made that the individual time and temperature dependent enthalpies in chicken and other meats demonstrate that while cooking, water loss increases with time and temperature, while the main water loss occurs during the first 240 minutes and at temperatures above 60 degrees Celsius. An observation can also be made that once the temperature of the chicken reaches the boiling point of 100 degrees Celsius, the temperature is constant as the water seeps out is converted to gas. The heat required to convert all the liquid to a gas is called the enthalpy of vaporization. So there you have it, how to cook fettuccine alfredo with thermodynamics. Thanks for watching!